Okay, guys, welcome back to day 8 of Gravitation. And today I'm sorry about the audio and the video. I'm in a different place, so we have to go with this. I'm going to discuss the same things yes, like in the last class I was discussing about the variation of gravity with height and depth. As far as I remember, like for a planet, the radius is r. From this point at a height h, the acceleration due to gravity g height. Again, at some point g d, so at g depth. We talked about g depth and g height. We discussed all these things clearly in the last class. But before the ending of the last class, I gave this idea of g also varies with the rotation of Earth, right? So that is an important point. As Earth is rotating, g varies along with that. So this is also an important point. So let's talk about this thing. Like I said yesterday, if we are clearly looking, as we are all on the planet, not everyone has the same radius. If you clearly observe, this person has a radius like this person has some smaller radius, this person has some r1 radius. So not everyone's going around with the same radius, that is for sure, but everyone's going with the same angular velocity. Okay. So to make this a lot more clear, instead of talking about radiuses, we all know these things. Can somebody tell me what these lines are called as? Can somebody tell me what are these lines? What do you call them as? Everyone's typing. Latitude. Everyone says latitude. Are you sure? Okay, everyone actually said latitude. So they are called as latitudes. So what the latitudes are basically like you take any line like this, it makes an angle theta with the line in the equatorial plane. Okay, so this angle is basically represented here. Let us say if this angle is 60 degrees, they simply say this is 60 degrees. The latitude is 60 degrees. So it starts at 0 degrees, increases 60 degrees, 80 degrees, 85, and at the topmost point, the latitude is 90 degrees. So this is how they simply mention the latitude. At what latitude are you at? So these are the ways to mention this. But we use this idea in a different form. I'll tell you. I'll show you how. Okay. Uh, the way we simply say this is the radius of the orbit, radius of the post people who are going around equator, which is also the radius of Earth. Okay, somebody is in the waiting room. Have to let them in. Very sad. Very very sad. Very sad. Very very sad. I think that's it. Guys, no more disturbances, please. I cannot allow more people. So let's talk about this. So where was I? I was talking about the radius of the people who are here. Let us just say, which is nothing but the radius of the Earth also. The radius of the equator, which is also radius of the Earth. So let's consider people somewhere around here in this region who are living in this region. The radius they are going around is, if you take Earth's radius and take the latitude, the angle, their radius is nothing but this, which is r cos theta, and this is r sin theta. R cos theta and r sin theta. We don't really need the idea of r sin theta anymore. We will be talking about r cos theta a lot. So I'm removing the part of r sin theta. So now let's talk about this only. The orbit that he is going, the radius of that person or people or space, whatever it is, that is r cos theta. So he'll be having a pseudo force m r cos theta omega square like this. For this person, it is just m r omega square. For this person, it is actually m r. Oh, the screen is stuck. Let me share it again. Let me just give me a second, guys. Please let me know if the screen is stuck again, okay? Yeah, so for this person, he's going around in a circular motion. He's going he's going around a circular motion like this for this person. He's going in a circular motion like this. So they won't, both of them won't experience the same amount of centrifugal force. So that affects the whole thing in a different way. Again, it is, yeah, affects the whole system in a different way. Let me show it. So for a person who is on the equator, for a person who is here, we all know that there is a weight mg acting on him, and now additionally mr omega square. So the apparent weight apparent equals to his original weight minus this mr omega square. That's what I'm talking about. Original weight minus this mr omega square. Okay. Mm, Now, so this apparent weight is written as mg effective, which means, sorry, mg effective. This is mg effective. So from this, they cancel out m and write g effective equals to g minus r omega square for a person who's on the equator. But what if the person is somewhere around here? To him, mg is acting in this direction. Mr cos theta omega square is acting in this direction. To him, the effect of gravity is in this direction, right? So you have to take the component of this thing along that. So how much is that component? Can somebody tell? Theta. This is also theta. So m r cos theta omega square into cos theta. I hope you're following it. So for this person, effective weight effective equals to mg minus mr cos square theta omega square. I hope you're getting the point, the whole point. So for a person here, this is the weight. For a person at some random angle, this is the effective weight. In the terms of, bah, the screen is stuck again. Why is this happening? So where was I? I'm sorry about this. Keeps happening. So because of, with the all rotation, for this person, effective weight has become, the G effective has become G minus R omega square. For this person, G effective has become G minus R omega square cos square theta. Okay, so definitely effective G is clearly affected here and here. And for a person here, it is not even affecting. There is no mr square omega because he's not even going in a circular motion. So his effective G is always mg. His effective G is always mg. I mean, effective G is always just G. For this person, it is. So they simply say the G value, if only Earth is completely spherical, G has a highest value here. On the equator, G has the lowest value. Strictly speaking, I even remember the values to some extent. It is 9.79 meter per second square here. Here it is 9.83 meter per second square, I guess. So they take an average of these value and write it as 9.81, okay? But this is not real. This is not the original value either. Because on Earth, gravity's acceleration due to gravity varies from point to point in different ways. So first of all, Earth is not in a spherical shape. Strictly speaking, Earth is like slightly squished compared to a spherical shape. So Earth is not in spherical shape. There are so many quantities. There is so many ideas. There are so many different kind of densities. They can all affect. But we simply consider as Earth as a like a sphere and simply say things like it. This is 9 point. Sorry, here it is 9.79, the least. Here it is the highest. It is 9.83 meter per second square. So if you go to this pole and if you go to equator and and if you measure yourself with the same weighing machine, I'm clearly stressing this point because the weighing machines that they use at the poles and the equators, they are not the same ones, especially when it comes to sensitive materials, especially when it comes to materials which are very light and have to be precisely measured. They cannot use the same weighing machines. They cannot use the same weighing machines in both the points. Okay, that is a very important point. They actually make the adjustments according to these g values. Otherwise, you will always get wrong values. That is one important point. Now, coming to the next idea. Oh, why don't we look at some problems regarding that? Look at the problems 22, 23. 21 is the old problem. We've already done that kind of a model. Look at 22. Uh, find the height, find the height or which surface earth the body is weight becomes half. So he's clearly asking at what point. Why don't we discuss these things here only? So in the question number 22, he's asking at what height, like you have a planet, at what height compared to this thing a person would weight only half of, so which means here it is mg, here it must be mg by 2. If the g is mg by 2, what is the height? That is what is asking. So question number 22, 23, what is the acceleration due to gravity on the top of Mount Everest whose height is given? Like again, in this problem, is clearly giving the height and is asking the acceleration due to gravity. Again, this is not a precise way to put it because, like, if you're considering Mount Everest also being a part, the screen has stopped again now. I've never faced this kind of a problem. Okay, so if you're considering Mount Everest also, it shouldn't be a perfect sphere, right? But they simply consider that and they simply write the acceleration due to gravity at some height. Okay. Again, I already told you there are two ways to do it. G at a height equals to gm by r plus h whole square. This can be used all the time. Or you can simplify it by saying g at g normal at g surface or normal g value, g at a height equals to g, normal g value to 1 minus 2h by r. This is an approximation, I already told you. You can use this approximation or you can use the original value also. And then comes the depth idea at t. This you can use anywhere. G at a depth equals to normal g into 1 minus d by r. This can be used anywhere. Maybe that's what he's asking in the next problem. Find the acceleration due to gravity in a mine of depth 640 meters. This here you can happily use it. The 25 body weight spring. Yeah, how much does he is giving the weight at North Pole? He's asking the weight at equator. Account for Earth rotation. So this is what is asking the question that we just discussed. He is giving the value of weight at pole, and because of rotation at equator, the value is g minus r omega square. G effective is here. The value is just g. So he gave the weight here. He is asking the weight here. Okay, so my voice is cracking, guys. Is my voice okay for you people? Okay, fine. So Aditya, it must be on your side. Some maybe it must something wrong on your side maybe. Anyway, let's keep this session very small. Okay, like I don't want to spoil too many things at this clarity. Let's just keep this session very small. I'll just discuss this bit, and we'll discuss the rest of the things tomorrow itself. Okay. Look at 26. A body stretches a spring by a particular length at Earth's surface at equator. At what height above the South Pole it should? Yeah, this is a good question again. Let me draw it properly. So he says at surface a body stretches a spring. So they are basically measuring some weight. They're basically measuring some weight at this point using a spring balance. So spring balance is stretched because there is weight. But the weight acting here is mg minus mr omega square. So this equals to kx here. If you want the same amount of x, that's what he's asking. If you want the same amount of x, but at the pole, from to a height, at the pole you only get mg only, right? But at what height do you get the same expansion? So at some height you have m. How do I write it? Should I? Yeah, we can approximate this value. Mg into 1 minus 2h by r. So at some height you get this weight, and you should equate the weight to this thing, and you have to find the height. That is what he's asking in the problem. So that is the question of 26. Okay, guys, I understand voice is cracking a little. I understand. We will close the session just by discussing these problems. Okay, I don't want to ruin the idea of satellites today. So I'll just end the session early. Now look at 27. At the rate, so rotate. Now look at the questions 27. At what rate should the Earth rotate so that the apparent G at the equator becomes right? This is a good question, guys. I remember someone asking me this question, and I gave a very silly answer. So somebody asked, what if Earth starts rotating? Like Earth basically rotates for 24 hours. Right? For full rotation, it takes 24 hours, right? Somebody asked, what if it starts rotating much faster, like 30 times faster? What if Earth starts rotating to 30 times faster? The question they were expecting me to say is basically they asked me to. I mean, like they were thinking of. This is a question in some interview, so I didn't attend the interview. Someone else attended the interview, and they asked me this question. So they're expecting the answer like we get paid daily because the Earth is rotating 30 times faster. One day you complete 30 days. You basically complete 1 month. But that is not the stupid way to do it. Like the proper way to answer, I would say, because of Earth's omega, high omega, you will get high mr omega square. Mg and high mr omega square, you will feel much lighter because you will be getting a much heavy pseudo force. You will feel much lighter. So that is what happens actually when you rotate faster. Okay, but in this problem, in the problem in Hesiwama, he's asking at what omega should you rotate so that the g effective here must be 0, which means g minus r omega square must be equal to 0. This is what he's asking. So from this, he's asking the value of omega. Okay, try to calculate that value. He's directly asking the omega value, considering g minus r omega square equals to 0. Okay, now that is done. And question number 28 is also an interesting one. Okay, so there is a ship going on the equator. There is a ship going on the equator. Already Earth is rotating with omega, let us say. Now, if the ship is also going in the same direction, it adds up with the Earth's rotation. So you will get V plus R omega as the speed of the ship. If the Earth is rotating like this and ship is traveling in the opposite direction, let us say, ship is traveling in the opposite direction, you get V naught minus R omega. Whatever the thing is, since the ship is going in a circular motion here and also circular motion here in the both the situations, what happens is Yeah, you can write m r omega square or m e square by r. So v naught plus r omega square by r, and here also m v naught minus r omega square by r. This is the pseudo force that is acting in both the cases. In one situation it's like this, one situation is like this. So I will write G effective now. So G effective will be G minus mv square by r in one case, in both the cases, but G effective when the boat is going with the direction m, v is v naught minus r omega whole square by r. In the second case, the case 1, case 2, where G is G minus M, V naught plus R omega whole square by R. You have to calculate both the G effectives for this problem in 28. Okay. And he's asking about the time period and all. You don't know the time periods for now. For now, just remember the formula. You might have seen this formula in schools 2 pi root over L by G. That is a time period for a simple pendulum. Here you need to put the G effective. What are the G effective that you are getting in both the cases, case 1 and case 2? Okay, so that is how you basically solve these kind of problems. From this problem onwards, it's a different thing. 29, 30, 31, there are different problems. But I just wanted to discuss the G effective problems today. Okay, and guys, since oh, you weren't taught about this thing. Like you might have, they might have given this formula at least. The time period of a simple pendulum is 2 pi root over L by G, where L is the length of pendulum, G is the acceleration due to gravity. Even it wasn't taught, I will discuss, definitely discuss this thing in the future topic, in the topic of simple harmonic motion, right? So in the topic of simple harmonic motion, I'll definitely teach that anyway. But in this problem, we just came across this formula, so I'm discussing it anyway. You don't have to worry about it. And guys, that's it. Like since the class is breaking, we'll just cut it down for today at this point. Maybe what 30 minutes, 20 minutes class. Tomorrow onwards, I'll be home anyway, so we'll have a better class from tomorrow onwards. So before I end the class, is there anything to say? Anybody? Are there any doubts? Yeah, Sharath.
Sir, you said right, sir, at the poles there's higher like there's higher pull than from the equator,
Right,
right?
right, yeah.
So can we say that the Earth is squished because of its own gravity?
Earth is what?
Squished because of its own gravity.
Yeah, I already mentioned this thing few days ago. Acha, acha, you're saying this squish, this kind of squishing. No, no, no. This kind of
Yes,
squishing
sir.
is actually happening because of the rotation. Like take some dough, maida dough. Okay, like you try to rotate it, tries to get stretched like this, right? Slowly.
Yes,
So it's
sir.
that kind of an effect, not because of G. Earth's gravity is not good enough to crash it or compress it. Earth's gravity is not, I mean, like, yeah, it is good enough, but not good enough to change its shape. There might be some effect, a small effect maybe, but not to that extent. Okay.
Okay, sir.
Is there any other doubts, guys, before I end the class? No, I guess. Alrighty then, we'll continue the session tomorrow. Hoping everything will be better tomorrow. All right. So thanks so much and bye bye.